In the last video, we saw a potential mechanism where if we reacted hydrogen bromide with this alkene right over here, that we can essentially add, we had the addition of this halide to what it was started as an alkene, and then it ended up as 2-bromopentane, as an alkane. But when we did that, we made I guess you could call it a somewhat arbitrary decision, or I didn't explain why we made the decision. We said, look, this hydrogen is going to be partially positive because this guy is so electronegative, and maybe when it's partially positive, it'll be attracted, maybe it'll just bump in just the right way into one of these carbons, and it'll maybe swipe its electron. We somewhat arbitrarily in the last video decided that it would swipe this guy's electron. But you could just as easily imagine a world where it swipes an electron from this guy. So let's draw a mechanism for that and just think about which one is more likely to actually happen. So what happens? So once again, this guy, let me draw all of his valence electrons. So there's the bromine. 1, 2, 3, 4, 5, 6, 7 valence electrons. You have the hydrogen. I'll do it the same color. The hydrogen has its electron right there. This is partially positive, and this is partially negative. The hydrogen might want to swipe one of these electrons away. Let's do it from this guy right here. Let's do it from this guy. So he has this electron right over here. So the other side of that bond, it goes to the hydrogen when the hydrogen goes near it, or maybe it's attracted to it. And when it goes to the hydrogen, then the hydrogen lets go of the electron that the bromine wanted all along because it's so electronegative. So then that electron goes to the bromine. So after we do that, what will it look like? What will be the next step in our reaction? And it will look fundamentally different than this right over here. So now what happens? So we have a carbon bonded to two hydrogens, and it only has a single bond to the other carbon, which is bonded to the original hydrogen right over there. The rest, let me write my hydrogens a little bit. Actually, let me write this whole thing a little bit neater. So you have your carbon bonded to a hydrogen and another hydrogen. And now it only has a single bond to this carbon right here, which is bonded to a hydrogen. And then the rest of the chain. Let me just draw the rest of the chain right here. And now this electron went to the hydrogen. The other electron that it was paired with is still with this carbon. So now this carbon is now bonded to that hydrogen over there. So this blue electron is now with the hydrogen. So let me draw. So the blue electron that was here is now gone over to the orange hydrogen. Has now gone over, let me draw a little bit neater than that. Has now gone over to this hydrogen right over there. And then the hydrogen lost its electron to the bromine. So the bromine originally had 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And then it nabbed an extra electron from the hydrogen. So now it will have a negative charge. It is a negative ion. It is bromide. It's a bromide anion, I guess you could call it. And since this guy lost an electron, he had 4 valence electrons, lost one to the hydrogen. He now has a positive charge. He's a carbocation. He's a carbocation. And then from here, so notice the difference. Before, this guy lost the electron, and so the hydrogen bonded to this carbon. In this situation, this guy lost the electron, so the hydrogen bonded to the other carbon. And so you can imagine from here something very similar happens as what happened in the first video, but now it happens to this carbon right over there. So let's do that. This carbon is positive. The bromide ion is obviously negative. So maybe he'll want to swipe his electron away. So this electron then goes to the carbocation, and then it will form a bond. It will form a bond. This green one will go to the carbocation, and then this purple one still stays with the bromine. And so they'll have a bond. They're paired up. You can imagine it. So then we're left with, we have a carbon. We have our original hydrogens. We have this carbon, that hydrogen, the rest of the chain. CH2, CH3. And then you have this hydrogen right here that it bonded to. That was kind of our first step. And now the bromine has bonded to this carbon right over here. The bromine has bonded over to that carbon right over there. And we're done. This is another possible mechanism. This one we ended up with 2-bromopentane. right? Because it's on the number 2 carbon. Here we have one bromopentane. 1, 2, 3, 4, 5. Still 5 carbons. It's just the bromine is attached to the 1 carbon here, attached to the 2 carbon here. So we now need to think about, because at a first cut, these both seem like reasonable mechanisms. But if you did it experimentally, you would see that this is the one that you would really observe. I actually haven't done this exact experiment, so I don't know the proportions, but you're going to observe this one disproportionately. The great majority of the products that you see are going to be this one, not that one. And so the question is, well, they both seem like reasonable things to do up here. Why is this one so much more likely to happen than that one? It all comes from something called Markovnikov's rule. Markovnikov's rule. Nikov's rule. And there's a couple of ways to think about it. And when Markovnikov thought it up, or he observed it, it seemed to work. They weren't 100% sure about why it worked, but we can even think a little bit about why it worked. So Markovnikov's rule, a couple ways you could think about it. You could think of it as the thing that already has more hydrogens is more likely to get more hydrogens. So that's what happened here. This thing had more hydrogens on it than the right carbon right here. This right carbon had a hydrogen, but it had some other, I guess you could call it an alkyl group attached to it. And so the thing that had more hydrogens ended up with the hydrogen, and then the thing that had more groups, this character right here had more groups, right? He had one group over here. This carbon over here had no groups. He ended up with the bromine. So the thing that has more hydrogens ends up with more hydrogens. The thing that has more groups ends up with more groups. So I guess you kind of go more in the direction that you were going in. But that still is just, a rule. So, why does that make sense? And it all makes sense, or it starts to make sense, when you think about that in both mechanisms, we had to have a carbocation. Right? We talked about in the last video. Carbocation. We had a carbocation right over there. This is the left carbon being a carbocation. This is the right carbon being a carbocation. And Markovnikov's rule is all comes from which carbocation is more stable, which one has a lower energy level. And it turns out that the carbocation that is bonded to more, I guess, electron-rich molecules or atoms is going to be more stable. You can imagine that it has more things that, look, it's positive, but it has more carbons around it, so it can share some of those electrons. The electron clouds will help it out a little bit to be a little bit more stable. This one right here is only bonded to one other carbon, so not as much sharing. This is bonded to 2. So in general, when you're only bonded to one other carbon, you're called a primary carbon. And if you're a carbocation, this is a primary carbocation right here. This guy is bonded to 2 carbons, so he would be called a secondary carbon. Since it's a carbocation, it's a secondary carbocation. So this right here is secondary. So a secondary carbocation is more stable than a primary, and actually a tertiary. If you had another carbon group here or something else that had a lot of electrons around it, that would be even more stable. So bonded to 3 things, more stable than 2 things. And when I say 2 things other than hydrogen, and then more stable than 1. So Markovnikov's rule all is a byproduct of the fact that this carbocation is more stable than this one over here. And that's because it's secondary versus primary. Because it's secondary, it can kind of borrow electrons from some of its friends. It has more neighbors to borrow electrons than this one. And since this is more stable, this is more likely to happen. This is a more likely intermediate to have. This is a less likely outcome to have in general. And that's why you're more likely to get to this left product, the 2-bromopentane, than the 1-bromopentane.